in a speech a week or two ago. Well, that's the truth. Mark's one of our newer members and is really embracing the Toastmaster program. Today, Mark will be doing his second presentation for the club. Electricity is the lifeblood of a data center. Mark will explain how power flows through the data center and the different devices that make the electrical system robust. Join me in welcoming Mark Johnson.
Good. The hardest part of the speech is over. I got that thing to stand up. So tonight my speech is on power flowing through the data center. Power is really the lifeblood of a data center. Everything that goes on at the data center requires power. Without it, you would have no communication, nothing would work. So keeping power onto these computers at the bottom of this chart is they cannot be disrupted. They always have to stay on. So it's a very interesting study of how power gets there and how it works through the whole system. So I'm going to attempt to explain this to you today to let you know the basic parts of a data center and how they function. The first thing to keep in mind, though, is all data centers are not the same. They're built different. Usually they're built by a tier standard or they're judged by a tier rating. So a tier 1 data center is much different than a tier 4 data center. A tier 4 data center would be considered a very robust data center. That means dual sources of power, 2 sources of everything, all the way down to the computer. Just like I've drawn here, it has a power source on this side and a power source on that side. And it would have that all the way up to where the generators tie in. So that would be a very robust data center. The problem with a very robust data center is, one, is they're very expensive to build. So in today's world, very few tier 4 data centers exist. The other thing that hurts a tier 4 data center is that it's very inefficient, meaning that you have a lot of equipment that's just running, but it's not doing anything except standing by for something else to fail. The great part about a tier 4 data center, though, is it's very robust. The likelihood of it failing is very unlikely. So that kind of gives you the idea of it. But it's very interesting of how power starts on incoming into the building and how it gets down to the computers. And all these pieces have to kind of work in concert with each other to be successful. So the first part that I wanted to talk about was basically the upper part, or the entrance of the power to the data center, and this is, we're talking about public utility and our generator building. These two things have to work together. So most of the time, public utility is carrying the load to the building. But upon a utility failure, step over here so you guys can see a little better. Upon a utility failure, there's an important first step that happens. So we lose the utility. Now there's going to be a timer that starts, and it's going to count to approximately 3. If power from that utility comes back on in 3 seconds, these generators do not start. We stay on utility. This allows us to not have a lot of generator starts, a lot of problems with power coming on and off to the data center. So we count to 3. Now, if that counter goes past 3, all the generators at the site will start up. And they come up to speed, and usually that takes approximately 20 to 30 seconds at the site that I'm at. That means that these things have to fire up, come up to full speed. Now, the interesting thing about alternating current is you have a positive and negative electricity, and we're dealing at my data center 13.2 thousand volts. So these have to sync. So as a positive wave cycle goes up, all the generators have to be positive at the same time. They all have to be negative at the same time. So there's a sync check relay that's going to make sure that as these fire up, they fire up at different intervals, but they run at a little bit different speeds, so they all catch up with each other and they all sync together. And once they all sync together, now we're going to switch over here to their generators, and these generators are going to carry the rest of the building. Now, when I said earlier that it's unacceptable for these computers to ever turn off, that really creates a dilemma for us, because If the generators take 30 seconds to start, the utility is lost, there is no power coming down this way. So how do we keep these computer loads running while this is taking place? And so what happens is the next step that I wanted to talk about is this UPS system here. So UPS in our world it's actually the abbreviation that we use in our industry, but it's really an uninterruptible power supply is what it's called. I've got a little bit of a drawing of one here. I wanted to kind of show you what happens inside of a UPS. So since we have alternating current coming from our generator or utility company, the first thing that I'm going to do whenever that power runs right into this UPS system is I'm going to run it into a rectifier, and that's part of this UPS system. So this rectifier, the thing that it does is it's going to transfer the alternating current to direct current. Then as the power flows right on through, I'm going to run it next to an inverter. And that inverter is going to convert the direct current back to AC current, and it's going to go back out and downstream to feed my computers. So at the point that I have transferred that to DC right here, direct current, I'm going to tie a bunch of batteries. And at my site, I have 120 batteries that connect right here inside this UPS. So at the time that I have a utility outage, as my power stops feeding here because I have no utility or no generator coming in here, my batteries are simply discharging and they're feeding through the inverter, and that inverter is making the AC. These batteries are getting weaker and weaker. At the same time, my generators are starting to fire up, and once they fire up, then I have power coming back into here. It's actually recharging my batteries, and some of it's going back, the rest of it's going back to feed the computer loads downstream. So that's basically how we get power transferred from utility to generator, and this is the job that these UPSs do during that transition phase. The next part of it is I wanted to talk about is a static transfer switch. And I've got a diagram of this that I drew. So a static transfer switch actually has two sources of power to it. It has a source 1 side, which is normally the primary side, and a source 2 side. A static transfer switch has two things called SCRs, or silicone controlled rectifiers. Basically, it's a fancy name for a really fast switch. In America, 60 cycles of power is what we have. In Europe, they use 50 cycles of power. That means that on a 120 volt circuit, it goes to a positive 120 to a negative 120, 60 times in a second. This thing switches, so it detects a problem upstream, and it will switch from source 1 to source 2 in 1/4 of one of those wave cycles. That is so fast, the computer never sees it. And so that's how we get back to this. So if I had, like in this example, if UPS-A decides to go bad, this thing's going to transfer over here to my redundant UPS so fast that this computer never seen it coming, and it stayed up and running. So that gives you some of the basic ideas of how power feeds through the data center. And the other thing that I wanted to talk about is just the design itself. So in this diagram, I have a redundant source of power, and I have a source A and a source B. So as you can see, if anything happens upstream, my static switches will switch over to this redundant source, protecting the load downstream. It's a very important design of data centers. This is what I typically see whenever I manage data centers. This is what I have kind of at my site today. It's a little bit more complicated, but hopefully I've given you an insight on how power flows through a data center, and a little bit of knowledge of how data centers are built and the robustness that's put into these things. Thank you very much.